Well, hey there. These are the notes from Tuesday, and that would be the latter part of Learning Target 4.1. And if you had me second or fourth hour, we did these notes. If you had me fifth, sixth, or seventh hour, I don't think you took these notes because I had to leave. And I'm guessing you probably didn't do a whole lot of much because I didn't have a whole lot ready for you. So you're going to need these. You left off and we were talking about the wave equation, which was the relationship between the speed of light, the frequency, and the wavelength of electromagnetic radiation. Now today we're going to talk about what's known as the dual nature of light, and so this is on your next page, which is that light acts both like a wave and a particle, or a photon, at the same time. And so that's kind of a weird, it's a weird thing to think about, but there were some things that were happening that led scientists to believe that light couldn't just act like a wave. There were some things that light did that made it act like a wave, but there were also some things that light was doing that was making it act like a particle. And because of that, we needed to make sure we recognize that in our statements. So that's where we came up with this dual nature of light. And so at the same time, light acts as both a wave, which we talked about, and then also a photon. And you have the definition of photon here. Photons are massless particles that carry a quantum of energy. And energy, when it's talking about a quantum, it just means a very specific amount. So it's a specific amount of energy. And that amount is measured in the unit joules, which is a capital J. The energy of a photon can be found if the frequency of the light is known, and that is by using this equation right here. The energy, E, of a photon is equal to H times nu, where nu is the frequency. And remember our units for frequency, you have a lot to pick from. You can say hertz, that's one acceptable unit. You can say waves per second. You can say per seconds. Or you can say seconds to the -1 power, which is the same as putting seconds in the denominator. So any of those units are fine for frequency. If you multiply that by this H value, that's going to give you the energy of a photon, and remember that's going to be in joules. And so this H we need to talk about, this is new. This is called Planck's constant, because this is the guy who kind of came up with this relationship, and Planck's constant is equal to 6.626 times 10 to the -34 joule seconds. That's a joule times a second. And so that is a second equation that we can use to learn some stuff and calculate some stuff about light, this time as a photon or a particle, and then yesterday as a wave. So let's do some of this. Let's do some examples. The first example we have here is, get rid of that. I put all the relevant information up here, so no need to rewrite all of this stuff up here. This is all what we just wrote down. Okay, so that's just there for reference. It says, what is the energy of a photon of light if it has a frequency of 1.17 times 10 to the 20th hertz? And so in this case, we can just use our E photon equation, which is equal to Planck's constant times frequency, because the problem is giving me a frequency in hertz. So this is easy peasy lemon squeezy. I'm going to substitute in 6.626 times 10 to the -34 joule seconds for H. And I'm going to put that in parentheses. And then I'm going to multiply that by, I'm going to use purple, the frequency, which according to this problem right there is 1.17 times 10 to the 20th. That's not a very good 20. Let me try that again. to the 20th. Now instead of hertz, I'm going to write the unit 1/seconds. Now remember, any of those 4 units is fine, but I'm just going to use this one to show you guys what happens to my units when I use this one. So if I multiply those two things together, I'm going to get an answer, and that answer is going to be, let's see here, 7.75 times 10 to the negative 14th. And if you look at your units, you have a seconds in the numerator here and in the denominator here. And so those two would cancel, and you'd be left with just joules. And so that particular photon would have an energy of 7.75 times 10 to the negative 14th joules, which is a very, very tiny amount of energy. But remember, that's for one photon, so that's okay. Just so you guys know, too, this frequency right here, if you look at your chart from yesterday on page 2, that would correspond to the energy of the frequency of a gamma ray or a gamma photon. And so that would be the most frequency, one of the highest frequencies you could have. So that would also indicate that this is one of the highest energies that you could have. Let's do another one. Here we have the same information up top, but this time we have a question that's a little bit different. It says, what is the energy of a photon of light? 0.00 times 10 to the negative 7th hertz. Now there's a problem in this problem, and that is because of Mrs. Sharp, and that's because we don't measure wavelengths in hertz, we measure them in meters. So I'm going to go ahead and change that. So this time we're not given a frequency, we are given a wavelength. And so we can still do this, but when we write down our equation, E photon equals h times frequency, we have a little problem. We know h, but we don't know frequency. So we're trying to find the energy of the photon. We know h, it's 6.626 times 10 to the negative 34, but we don't have anything we can substitute. It's not telling us the frequency this time. So what we're going to do instead is use our C equation to find the frequency, and that's what we were doing yesterday. So if I line up my C equals wavelength times frequency, I could solve for the frequency and then plug that in up here. So I'm going to do that over here to the right. So I'm going to take C equals wavelength times frequency. I know my C, it's 3.0 times 10 to the 8th meters per second. I know my wavelength, it's 7.00 times 10 to the negative 7th meters, and I am solving for frequency. And so that would mean dividing each side by 7.00 times 10 to the negative 7th. Meters. That would cancel, and according to what I calculate there, that means that my frequency comes out to be 4.28 times 10 to the 4.29 times 10 to the 14th hertz. So since I know the frequency now, I can plug that into my frequency right up here. So I found the frequency there. It's 4.29 times 10 to the 14th. I'm just going to plug that in up top. So I'm going to clean this up a little bit here. So now I can take my E photon equation, and I can still use my 6.26 times 10 to the negative 34. That hasn't changed. But now I also know my frequency, which is 4.29 times 10 to the 14th. And remember, hertz is the same as 1/seconds. So that our seconds cancel. And if I multiply those two values together, there's my h, there's my frequency, I should get the energy of that photon. And when I do that, I get 2.84 times 10 to the negative 19th joules. And that is quite a bit smaller than our last photon. Our last photon had times 10 to the negative 14th, which would be 10 times 10 times 10 times 10 times 10 more energy than this guy right here. And that makes sense because the last one was gamma, so it has the most energy for radiation. This is on the order of, this would be like purple light. So purple light has a wavelength of about 7 times 10 to the negative 7th meters. Actually, that's not even true. It'll be less than that even. Anyways, this is a lot less. So, anywho, this gives you an idea of how to do those problems so you can finish those practice problems 4.1 and 4.2 that are posted on Edmodo. Have fun!